Okay, hello, this is Physics 1A for March 1st. We're going to pick up where we left off last time and solve a few equilibrium problems that involve torque. This is the problem we were working on at the end of class. You have this table here, which is this purple thing, and it's being pulled to the right with a force of 20 pounds. And the first thing we were wanting to do is to find the coefficient of kinetic friction and the normal force on each leg. So we did manage to do half of that. We solved for the coefficient of kinetic friction right here. And we did that by labeling all of our forces. We'll just go quickly back through what those were. So there's the force P that goes this way. We said that there would be normal forces on the front and the back legs, N1 and N2. There's also going to be friction at where those legs hit the ground, so here and here. And in addition, its weight, it said its center of gravity was 1 foot directly below the table. So I guess I never labeled this on here. We'll need it for this time, I think. But this distance from here to here is 1 foot. And then the 4 feet, this one, is the distance across the top. So it's 3 feet tall. It's 4 feet square on the top. And then the center of gravity is right here, where the weight's being pulled down 1 foot below. Okay, so we solved for the coefficient of kinetic friction by using this kind of normal method of the conditions of equilibrium. So net force in the x direction equals 0, net force in the y direction equals 0, and we haven't done this one yet, but we will this time. So in the x direction we had P and the friction forces, and we reduced that down, and eventually we found this relationship. And then over here, weight is equal to M1 plus N2. But we would like to find what the value of the normal force on each leg is. And while we were able to find the coefficient of kinetic friction just with these two equations, we can't use these two equations to find the normal force. So we need another equation. We need the torque equation. So let's go ahead and write that down. And the first thing to ask would be, when you use this torque equation, you get to pick an axis about which you're going to sum your torques. And so you all tell me, what would be a good point to select for summing the torques here? What do you think? What kind of axis of rotation should we choose? Oh no, so we want to pick an axis of rotation. Which one are we going to pick? When we say sum the torques, you can't just start summing torques. You got to pick an axis. So which one are we going to, on the ground? Okay, but where? Could we put it here? Do we put it here? Do we put it here? Here? We can choose any point we want, right? Bottom left? Okay. We can do that. It's a decent choice because there are two forces that are at that point, which means when we sum torques, we're not going to get anything from those two. So we're only going to have to worry about the weight, this force, the normal force, and the force P. All right? So let's go about doing that. So if this is our axis of rotation, right here, yeah, we can use black, I guess. Then we're going to make, let's see, how many forces do we have? We have 1, 2, 3, 4, and this one are going to be clockwise. So we'll make clockwise positive. This is just a choice. And, let's go through each one of these. What's the easiest one to start with? Let's do the normal force N1 first. What should I write down for N1, for my torque? We need the distance to where that application of the force is, which is going to be 4 feet, right? So we'll have 4 feet multiplied by the force itself, which is N1. And then normally you'd multiply by the sine of the angle between this distance and this here, but that angle is going to be 90 degrees. And the sine of 90 is 1, so we don't need to write that. I said clockwise is positive. What direction is this N1 going to torque the system? Is it going to be clockwise or counterclockwise? And again, you think about this right here. Imagine there's like a lever going here and you're pushing up on the lever. Yeah, it's going to be negative because it's counterclockwise. That's right. Okay. All right, what's next? Let's do F1. So for F1, we're going to write down the distance to that force, right? Which is, again, 4 feet. And then we'll write down, just to remind you, this is our definition of torque. Torque equals RF sine theta, where theta is the angle between the R and the F. So for F1, we'll have 4 feet multiplied by F1, and then times the sine of, what's the angle between those right there? The angle between F1 and the distance from here to here. It's 180 or 0, right? We can choose either. So I'll just use 0. So this is just going to be a total of 0. That force isn't going to cause any torque because it's pulling right on to the axis right there. I'm going to make some more room here, I think. We'll shift all this. We're going to make this a little bit smaller. Just tuck it under here.
Sorry, can you repeat how you got 0? 0 degrees, right?
Yeah, it's either 0 or 180. If it makes more sense to you for it to be 180, that's fine. But
Yeah, I see. Okay, I was wondering why not.
So the thing is that remember with the sine, the sine of
Yeah, no, I understand. Yeah.
I'm going to go ahead and write it out. The sine of 180 minus x is equal to the sine of x. Right, so just remember that. Why we put a negative here? The negative sign here is because I made clockwise positive. And this normal force N1 is going to tend to rotate the system counterclockwise. That's why that one's negative. Does that make sense, Chris? Again, if it doesn't immediately make sense to you, you basically say you got an axis here, and if you draw a line from here to here, imagine that line is like a lever, and that lever is free to pivot about this point. And then you think, okay, what direction would the normal force push that lever? Well, it would push it counterclockwise, and so I'm making it negative. Okay. Now, the last two are really kind of tricky here, but we can use something we learned last time. So what do I need to do for, let's do the force P. Let's do this one, okay? Now, if we want to use this definition for torque, what we would need to do is we would need to draw a line from here to here, right? That would be our position vector. And then we would say P times that length, which I believe would be 5, right? This is a 3, 4, 5 triangle. So this is going to be 5 feet long. Also, we'd also have to multiply by the sine of this angle right here, which, I mean, I know what it is. It's going to be like 37 degrees, but there's actually an easier way to do this, and it'll give you the same answer. So what should we write down for the force P? So we've got the force, which is P, and we need to multiply by a distance here, right? And if you think about the method we talked about last time, which is called the lever arm method, can anyone tell me what would the lever arm be for this force P relative to this axis? Okay, so you're saying 4 feet because you're thinking that this force is 4 feet away from this point, right? That's not exactly right. Someone else want to try? 3 feet? That would be the other distance, okay? And how do we know it's 3 feet and not 4 feet? So the way you do this is you imagine that you take your force and you just extend it left and right as far as you can. So you basically go like this. You just like draw. If you were on a piece of paper, you just take a straight edge and you draw a line like this right here. And then I made that way too long. Sorry. There we go. Oop. There we go. And then you say from this line, how far is it to the axis? And can you all see that that's 3 feet? Yep, shortest perpendicular line between the line of force, yep. So for this, it's going to be 3 feet times P, and that force would tend to rotate clockwise about this one, right? All right. Last is the weight. So for the weight, we're going to have the force, which is the weight. And now that we've said that, can you all just think for a moment? What's the lever arm for the weight going to be? Don't answer too quickly, just kind of think about it. You've got your line of force right here, and we just want the shortest perpendicular distance to that. What's that going to be? 2 feet. Yep, that's right. Yeah, so 2 times W with a feet. You need the feet. Hopefully you're okay with this tick mark representation for feet, because I really hate writing FT for feet. It's just a really ugly looking symbol that almost has like a plus sign in it, at least with the way I write my letters, so I don't like writing that. Okay, that's it, right? These should all sum to 0. Remember that F2 and N2 are going to have a lever arm of 0. So that's all we got to do right there.
Can you explain that perpendicular thing? I'm sorry.
We'll say it again.
Can you explain like why we do the perpendicular thing?
Why? You mean as opposed to doing the other one?
Say again?
As opposed to writing it out this way?
Yeah, because you did perpendicular, and then you did like 3P. Like, I'm trying to understand why the perpendicular for P.
So do you remember we talked about the lever arm method for calculating torques yesterday?
Oh yeah, with like the right hand.
The right hand rule is something else. The lever arm method is where you have an axis and you've got a force, and to find the torque, you use the shortest perpendicular distance and you multiply that times the force. It's just a different method for getting torque. You always get the same answer whether you use this method or whether you use the lever arm method that we just used here. The lever arm method just happens to be a lot neater. There's no signs.
Yeah.
You understand?
Yeah.
Okay.
Thanks.
No problem. All right, so our goal here was to find the normal force on each leg, and now we have an equation that only has one unknown, which is the normal force, because I don't remember who said it, but by selecting this left edge for your axis, we eliminated one of the unknowns, which made that a really good choice right there. We also could have chosen this point right here if we wanted to. And it may not be obvious, but one of those 2 points would absolutely be the best choice in this case. Okay, so we're solving for N1, so let's just, we've got 3 feet times P. P was equal to 20 pounds in this part. And then plus 2 feet times W, and W is 50 pounds. And then I'm going to move this piece to the right-hand side. 4 feet times N1 right here. And now we just need to divide everything on the left-hand side by 4. This is 60 plus 100, so that's 160. And now I have to actually write the foot out, foot-pounds. And we just need to divide that by 4. And 160 divided by 4 should be, what, 40? Like that. And then we can come back over here and find N2 from that equation. Anyone have any questions? While you're all typing, I'll go ahead and solve for N2 from here. So right here, let's see. This says that the weight minus N1 should be equal to N2. And our weight was 50 pounds. And from that, we're going to subtract 40 pounds. And we'll find that the normal force on the back leg, or the left leg up here, is equal to 10 pounds. So the force on the front is larger. This is something that we included in the diagram because I asked you all last time that to tell me which one you would think is bigger, and you said that this one would be bigger on the front, and it turns out that's right based on the calculations. It also should kind of make sense that since you're pulling from the top up here, the front leg is going to dig more into the floor. The one question is, why is there a sign 0 right here? I put that in just to show that when I found the torque for F1, that force is basically pushing onto the axis, so it's not actually going to cause any rotation. This would be like you take a bicycle wheel or something like that, turn a bike upside down so the wheels can freely spin. If you just push straight down on the wheel, straight toward the axis, and that's not going to make the wheel rotate, right? Does that make sense?
Yeah, that makes sense, actually.
So that's where the sign 0 is coming from. It's just I mean, it comes from this equation, right? Technically, I don't know if this makes it any clearer, but technically every one of these terms should have had sign something. Like the first term here, N1, we could have written 4 feet times N1 times sine 90, but you always have to include the angle between, your radius vector and your force. Okay, so Andrew, can you see why that's 0 in this case? Or 180, you can write whatever you want to. I could have written sine 180 too. Sort of. I mean, this is the definition that we're using, right? You take a distance from the so remember what these things represent, Andrew. R is the distance from the axis to where the force is. Would you agree that that's 4 feet for F1? Can you see that part? Okay. And then the next part you have to do is you add the force in, or multiply the force. And the final part is sine of an angle, right? Sine of theta. What is theta? Theta is the angle between R and F. So the angle between R and F is basically 0. Because, R is this line, and F is this line. There's no angle between them, right? Now, if, for whatever reason, if there was an angle, we would have included this little angle right here. But, yeah, there's no angle. Okay. Now, I don't know if I want to do this second part or not. I actually don't, because the next problem is going to cover kind of the same idea. And, yeah, I think we're just going to skip this last part right here. But I will say that we'll read it and talk about how you would do it. Find the minimum coefficient of friction such that the table is on the verge of tipping when being dragged at constant velocity. If the table's on the verge of tipping, that means that it's probably going to tip this way, like upwards, because you're pulling to the right here. And if it's just on the verge of tipping, what's going to happen to this force on the back leg? What would happen to this force back here if it was just on the verge of tipping? It doesn't mean the normal forces have to be equal. If the normal forces were equal, okay, the situation where the normal forces are equal would be when the object is just sitting at rest. It would go up into the air, exactly. So what would happen? So the normal force is a contact force, right? So what would happen to that contact force if there's no contact? The normal force would go to 0, right? Exactly. So both this force would drop to 0, and gotta hold Alt to make it not do that. And then there'd be no friction, basically. So that's how you do part B. It's really not, now that we've done part A, it's really quite easy. You just get rid of all of these forces right here, and you just do the exact same problem. P becomes an unknown because that's, well, yeah, P changes, basically. And the mu changes too, so you have to Okay, so we're going to do another problem that covers the exact same idea, and you'll see at least one of your one or two of your homework problems are going to have the same thing in it. Okay, so, I think I just put that problem directly below it, right? Left a whole bunch of room. So now we want to try this one. And what I'd like for you all to do is to... Oh, what's going on? I can't... What's happening? Well, let me click on... Oh, that's really weird. My mouse is down here. Is this because... What's going on? Well, while I figure out what's going on, try to read this problem right here. What is going on? This is all really weird. I'm closing this program. Read the problem, and we'll be back in a second. Okay. I should probably pin this to the taskbar, right? Okay, let's see if it'll let me click it now. It did. Okay. So I want you to read this problem, and I want you to draw a free body diagram, and then we'll talk about it. After you've drawn the free body diagram, you can try, if you want to solve the rest of it. Is that enough time to draw all the normal forces and maybe try to think about it? Let's see. So what are the forces acting on this box as it tries to slide down the plane? Normal, weight, kinetic friction. There's no static friction, just kinetic in this case, because it's sliding. It's sliding down the ramp at a constant speed. If it was sitting still, you'd have some static, but yeah. Okay, so we've got weight. The weight should be drawn right from the center of the object. We don't have any reason to think that the top is heavier than the bottom or anything like that, so we're just going to assume it's uniform. So we've got our weight vector that goes down like that. And then we're going to have a normal force and a friction force. So the normal force I'm going to draw right from the center, right here. And I guess we'll make it as big as we want. I'm not going to worry about like scale in this problem necessarily. Although I probably could actually, now that I think about it. Let's see, is that long enough? It's almost long enough. All right, I said I wasn't going to worry about it. We'll go ahead and worry about it. This should be about as long as, well, I'll show you in a second how long it should be. It should basically be about as long as the y component of this weight. So there's our normal force. And then our friction force should be kind of pointing along the bottom edge. So we'll draw the friction force back like that. And this one needs to be a lot shorter. It needs to line up like, yeah, that looks about right. So there's our friction force. That's F sub k. We could probably just call it F, if that's okay with y'all. As long as you know that it's a... Now we'll call it Fk. Doesn't hurt. Okay, and that's it. Those are the only forces that we have, right? All right. So the first thing it says is to find the angle theta. So given the information that we have, I realize W is used in this problem to represent the width of the box, isn't it? So maybe I should just call the weight mg. How about that? Let's do that. Let's just call the weight mg. Could call it force of gravity or something, I guess. All right, so we want to find the angle theta here. Now, like I've said before, if you're just like sitting there thinking, wait, how do I find theta? What do I do? That's not really going to get you anywhere. Like, just trying to solve the angle is just too hard if that's the way you're thinking about it. So, not knowing what to do in advance, what do? How do you solve for that angle without directly solving for it? XY, there you go. So that's one of the things we need to do. We need an XY axis on here. So I think the simplest thing to do is to make the direction of the plane to be one of the axes. So we'll make this direction the positive X direction. And then we'll make that direction upwards to be the positive Y direction, like that. Now that requires that we break our vectors up into components. The friction force points along the negative x-axis. The normal force points along the positive y-axis. So it's just mg here, the weight, that we need to break up into components. And in order to do that, what we'll do is we'll just do what we normally do. We'll just drop a line from here down to here. It's going to be its y component. I'll try to straighten it up a little bit. And then we'll use blue. Okay, we used blue for that one apparently. We'll use green for the other one. Oh, I hate the way this tool works. It's so weird. Okay, that will be green. And this should really come right up to there. And this should be a right angle right here. So those should be our components for our mg force. And since it is this, we'll write it right there. So then the other thing we need to do is to figure out which one of these angles to use. Now, I've shown you all how to do this before. I'll go through it again, but the simplest way to put it is that if this angle right here is theta, then this angle is 90 minus theta. So that means that this angle up here needs to be theta. But there's kind of another way to do it too. If you know that in the triangle that I have here with the blue and the green legs and the red hypotenuse here, if you know that that triangle has to have this same angle theta somewhere inside of it, as long as you've drawn everything with like a straight edge or a ruler, then you should be able to visually see which one of the angles it is, as long as you make your angle thin enough. So what does it look like to you? Does it look like it's this angle or the upper angle, the bottom angle or the top angle that would be equal to theta? Just visually, which one does it look like?
Upper.
The upper one, right? It's really obvious, right? So there's nothing wrong with doing that, you know? If you just don't know, just being like, which one does it look like? And that will only work if you make everything with rulers and stuff, but... and also, you don't want to make this angle 45 degrees, because then you won't be able to tell, right? But as long as you make it less than 40, it should be pretty clear. Okay, so that angle is theta. That means this side over here is going to be mg times which trig function? Sine or cosine down here? Sine? Yeah, because it's opposite, right? And then this one by default then has to be mg cosine theta. So there we go. That green line doesn't look quite parallel to the x, does it? But I'm just gonna ignore that for now. Okay, so now we can use our equations, right? We can use our... Okay, and again, this is like, we don't really know how to solve for theta, so we do what we know how to do, right? What we know how to do is this. We know that's true, and we just see where it takes us, right? Okay, so in the x direction, we're going to have mg sine theta going in the positive x direction, minus the friction force, Fk. That should be 0. In the y direction, we have the normal force pointing up, and then this mg cos theta pointing down. Okay. Now the next thing we can do is we can use the fact that the friction force should be equal to mu k multiplied by the normal force. And then over here we have normal force is going to be equal to mg cos theta. We'll take that normal force and plug it into this equation here. Oops. Okay. And then what happens is that our weight cancels out right here. And we end up getting that sine of theta divided by the cosine of theta ends up being equal to mu sub k. And that means that mu sub k is equal to, what's sine over cosine equal to? Tan, yeah. And that means that theta is equal to the arctan of mu sub k. Now, that may be kind of hard to read. It's like arctan of something that's like a Greek letter with a subscript. That might be kind of confusing. So let's pick a value. What's a good value to pick? Well, if we pick 1, the angle, what would the angle be if we picked mu k equal to 1? What would the angle be? What's the arctan of 1? 45, right? Okay. Let's not do 45. That's kind of boring. What if we choose like, I don't know, what's a good mu k? What if we just choose like 0.5, I guess? It's probably fine. What would the arctan of that be? I don't know that one. Arctan of 0.5. I get 26.56. Yeah, 26.6, let's say. If we chose that, we would get an angle which is equal to 26.6 degrees. Okay. Now, I'm just putting that in there so you can get a feeling for how this quantity, mu sub k, is going to relate to the angle right here. And then I guess one other thing to think about is it reasonable that the angle should be related to the coefficient of friction? The condition we have in the problem is that the block slides at a constant speed, right? So in order to get the block to slide at a constant speed, it depends on what? It depends on the angle, and the angle depends on how rough the system is, right? So we can decide what number for mu we can use. Well, this is just an example problem, Andrew. There's no actual numbers in it, so I just picked one so that it wasn't so mysterious. Like, I'm just saying, like, if this is the answer, this is the right answer to part A. It's just kind of confusing to look at that, you know? And in general, when you have a problem and you're given a value and they don't tell you what the value is, you are free to make up a value for it if it makes the problem easier for you. Does that make sense? It's better to use something small. Well, mu k is always between 0 and 1. But yeah. But really, that's a really good question because it allows me to talk about that. Like, you're going to have tons of problems in your homework where, like, there's going to be things they give you that are going to be, like, they won't tell you the value, you know? Especially when we get to the energy section, there's going to be problems where they don't give you the mass of the object. And the reason why they don't give it to you is because it's probably going to cancel out somewhere in the calculation. That being said, just because... Yeah, the lab manual. The lab manual has tons of problems like that. Exactly, Kelvin. And I just want to make sure it's clear that, like, you can choose any value you want to. Usually what I do, if I don't know if I don't understand something, I make whatever unknown just equal to 1, you know? Just make it equal to 1, and then it just cancels out in all the calculations, you know? So, okay. Anyway, we're done with that part. Now, this is the real... That's an interesting solution or whatever, but the real reason we're doing this problem is the second part. Because you're going to see problems like this show up in your homework, and personally, I remember when I was doing these type of problems, I didn't understand what this meant. It says, find the minimum ratio W over H for no tip. That is to say, what's the minimum ratio we can have of the width to the height such that it doesn't tip? And let's kind of think about what this means. What would happen if the height is really tall but the weight is really skinny? Like, say you took, well, let's use a really extreme example. Say you took a ruler. Rulers tend to be really thin and really long, right? And you put it on its edge, on the thin edge, and you tried to get it to slide down a ramp like this. What would happen? It would just tip over, right? Because the taller the object is, the higher up its center of gravity is, and eventually it'll just start to tip. On the reverse side, if the width is really wide, but the height is small, there's basically no chance that it'll tip. Again, think about a ruler, but now put the long side down flat right here along the plane. There's no way it's going to tip over, right? There's no way a ruler laid down flat could even possibly tip over. It's ridiculous to think about, right? So, unless, of course, the angle was really steep, right? If the angle got really, really, really steep, you could conceive of it tipping over maybe, right? That's possible, right? So there's a clear relationship between the angle, the coefficient of kinetic friction, we already saw that relationship, and these two things right here in terms of whether or not it's going to tip or not. So we need to figure out how to handle that. Okay, so how are we going to do that? Let me come over here and actually label our picture. So this side is the W side, this side is the H side. What would be happening if this object was sliding down the ramp and it was like just on the verge of tipping? What would we need to change about our free body diagram to indicate that the system is kind of about to tip, basically? What would it be doing? What would happen with these forces here? Is there usually a second delay on the video? There's two things going on there. One of them is we're on the internet. Number two is my internet connection's bad. I don't know what y'all's internet connection's like, but the other thing is that Discord is under massive amounts of load during this pandemic, and I've noticed in other times that I've used Discord that sometimes there can be these kind of lags. So if there's something you miss, you can always go watch it on YouTube later. Just skip to the part, and that's not the best solution, but it's the best we can do, I think. Okay, so the normal force would be approaching 0 again. Okay, so that's a good thing to think about. So this normal force is definitely going to change. It is the thing that's going to change if it's about to tip. But unlike the previous problem, this object, it doesn't have legs. Like, the previous problem, we had, like, legs, right? And those legs, we could say, oh, well, all the normal force is going to kind of show up on this front leg right here, and there's going to be 0 normal force on this back leg. That's what we did in the previous problem, right? Well, we can do something similar here, but instead of saying that the normal force is just on one part of it, on the one leg, we can say, well, really what's going to happen is that the normal force is basically going to shift to the front corner. Oh, no, I can see this isn't exactly straight. That's what's going to happen. The normal force is now going to be on the front corner. Also, if I can grab it, the friction force will also be at that location as well. Because now, if it's just on the verge of tipping, you can imagine that it's about to topple, but then it slides, and then it's about to topple, then it slides, like as if it was wobbling down the ramp, so to speak, right? Okay, but not really wobbling, because we want it to not tip at all. In that case, the normal force and the friction would basically go to the front corner. Does that make sense? Now, I know that you all have a problem that's similar to this. It's not exactly the same. I'm not going to... sometimes I'll assign problems that are very similar to what we do in class. The difference in the problem you do is just that instead of something sliding down a ramp, you've got a person that's got a rope, and they're trying to tip it over, basically. And the question is, what's the minimum force they need, or what's the point of application such that it will just tip over? You can use the exact same idea for that problem, basically, where you put the normal force and the friction force in the front corner, and you just go from there, okay? So that's generally the strategy for these type of problems. And that's the main reason we're doing this one. Okay. Does anyone have any questions before we start to solve it now? Yeah, you'd have tension. Yes, Hudson, that's right. mg sine theta is like the pull, exactly. Exactly. Now we need to solve this. And one thing, let's just ask, do either of these equations change? Do I need to go back and redo what we did in the first part? No, because they didn't change directions. They just changed where they were applied. So the only thing that would be affected would be our other equation, our torque equation, right? Only the torque equation, exactly. Kelvin, that's right. So let us see if we can fit in here a torque equation. So we know what the equation looked like. It's net torque is equal to 0. We know we need to pick clockwise and counterclockwise something to be positive and negative. You'd only have tension if someone's pulling it, Philip. That's right. That's right. Now this is the part of the problem I think that's the most tricky. What axis do we choose? What axis do we use? What do y'all think? It does matter in this one. There are many. I think there's more than one correct answer, but there are some answers that are wrong. In most problems, it makes 0 difference what you choose, but in this problem, you'll see that there's one axis that will cause some problems. I think there's only one that's bad. I could be wrong about that. Can anyone figure out what the bad one is? One hint I can give you is the center of gravity. That's a good choice. You'll see, Andrew. You'll understand when you see it and when I explain it. So what Kelvin said is a good one to choose. We'll probably end up doing the one you said, Kelvin, since that's the first one someone said. This one right here, right at the center, is a good choice. I don't know why you chose that, but it's a very good choice. What's one that would be... What about this one here? Why wouldn't we choose this one? The bottom corner. What's wrong with that one? Because it's not the center of gravity. That's not the reason why. what would the equation look like if we chose this corner right here? We'd have, we have to figure out, we have to draw a line from here to here for one. And then we'd have mg times the distance. Okay, Paige says, wouldn't it make the normal force unusable? Like, yeah, it would. It would also make this one unusable. So the problem with choosing this one is that you've got the weight right here, right? But that's the only thing that would show up in the torque equation. It's the only thing. Would just be the weight. And so you'd say the torque from the weight has to be 0. That doesn't tell us anything, basically, unfortunately. It doesn't tell us anything. So instead, we're going to use the center. Okay? We're going to use the center. Okay? So, what do we do for this? We need to pick a counterclockwise positive, I guess, this time, just to mix it up. So we're going to say counterclockwise is positive. We got two forces. We've got the normal force and the friction force. The normal force is going to tend to rotate the system counterclockwise. Can you tell me what would the lever arm... This is another example where the lever arm is really useful. What would the lever arm for the normal force be? In terms of H and W, or one of the other. W over 2. Yep. Not weight, this is width now. Again, if you don't remember, from the axis, you take the shortest perpendicular distance to your force, which in this case is going to be W over 2. Right. Okay, minus, we have the friction force down here, so F sub K, times, what is the lever arm for F sub K? H over 2. That's right. Oh, it's capital H, isn't it? Undo. And the weight, because it's pulling directly from its center of gravity, and we've chosen that for the axis, it contributes nothing. That's all we have right there. Anyone have any questions?
Wait, I'm sorry. Why no weight again?
What?
Why no weight again?
What's the distance from the point of application of that weight to the axis that we chose?
We can't. It's none, so it's 0.
It's 0. That's the reason why. So it's going to be 0 times the weight, which is 0, obviously.
Well, onto the sine theta, which we would use for the torque.
Once again, we're using the lever arm method here.
Oh, okay. So the lever arm means no sine.
No sine theta shows up. That's right.
All right, thank you.
No problem. Now that being said, just so that we're 100% clear about this, if you wanted to use the other method, what you'd have to do, just to indicate why it would be so hard, you draw a line from here to here, basically, right? Because that's the distance for both of them. And then you would need to know this angle, and you would need to know this angle. And the only way you could do that would be to write it in terms of W and H, which we don't really know. So it gets to be kind of messy, basically. But I promise you, even if you did that, and you reduced your equation down, your equation would eventually reduce down to this, if you can believe that. And you're welcome to try it if you want. It's the kind of thing I like to do for fun whenever we're teaching this class live, is to go through the long derivation while I'm waiting for people to solve things. So you're welcome to do the harder way if you really like math, and you'll show that you get the exact same equation. You'll take a lot of math, and you may have to use some trig identities. Not identities, but some trig relationships.
I'm sorry, Professor. Can you explain one more time how the weight is basically 0?
Why it's 0? Okay, so again, you understand that this is our axis, right?
Yes, 100%. So
the weight pulls directly down from that point. So what would the lever arm for the weight be?
Oh, just 0.
Right. So we would write the weight. We'd write mg times 0, basically.
We would not use mg cosine for the weight. We would just use mg.
You'd use just the weight itself, exactly.
Okay.
Yeah. Another question was, if we don't use the lever arm equation, how would it look? I mean, do you want me to write it out, Chris? We can. I can write it out. It's not. I guess it could help to indicate why it's so hard. So let's call this distance right here r, okay? And over here to the side, I'm going to say r is going to be equal to so that's what our distance is going to be. We're going to have to multiply both of our forces by that distance. And then we're also going to need this angle right here, okay? And I would say that that angle, phi, would be equal to, what is it, arc sine? The arc sine of w over 2 divided by r. Okay, and now when we sum our torques, what we would have to write is this. We would write normal force times r times the sine of phi minus friction force times r times sine of 90 minus phi, because we would need to use the other angle here, but I'm just going to simplify that by saying that that's actually the cosine of phi, because sine of 90 minus phi would be cosine phi. And then those would have to add to 0. Now I have to plug all this stuff up here in, okay? You'll see some things that happen that are kind of interesting now. So look at this one. This one goes in times, so r is equal to, Canvas Nationwide is having a technical issue. Oh, that's interesting. Okay. W squared over 4 times, oh, whoops, plus. You would all agree that this is quite a bit more time consuming already, right? I mean, if you look at the other equation, we're basically done, actually. Times the sine of phi. Now, this is interesting because this is going to be the sine of the arc sine of w over 2 over r. Such a long equation. Minus friction force times r it does look really... This is why we don't do it. I mean, I like this kind of stuff because there's some really cool things that end up happening here. So cosine of phi will be the cosine of the arc sine of w over 2 over r. If you can't read all of this, don't worry. Now, what's interesting is that when you do the sine of the arc sine, that gives you just the thing that's inside of it, right? But then actually, so the sine and the arc sine cancel, basically, right? But then actually, this r actually cancels with this one. So the first term becomes just n times w over 2, which is exactly what we have over here, right? And maybe I'll leave it to you to do this one, but you get the exact same, a similar thing that happens here. The cosine of the arc sine of w over 2 over r is actually equal to h over 2 over r, which cancels out with this, and you end up getting minus fk h over 2. So it's like, you get exactly the same thing, but it takes way more work, so that's why we don't do it. We just do the lever arm method as much as we can. Okay, and you'll definitely see some problems on your homework where that's gonna happen. Okay, so let's finish this problem. All right, so getting back to our original equation here. What do we need to do? We need to replace the friction force now. So this is going to be N. Here, let's go back to green, just to make sure that everything stays together. So we get N W divided by 2 minus mu K times the normal force times h over 2. Okay. And now, this is all equal to 0, so we could just put equals right here. And now what we can do is we can cancel out our normal forces here and here. And our goal was to find the ratio of w over h, so let's put w over h together here. You'll notice the 2's cancel too. So basically w... Oh. Oops. W divided by h ends up being equal to mu sub k. And that's the ratio. The minimum ratio ends up being exactly equal to this quantity. So for example, if it's equal to 0.5, if we choose 0.5 for our mu k, just to get an idea of what this even means, then the ratio is going to be 1 to 2, right? That would be an example. Some ratio of 1 to 2. It could be, for example, it could be like 4 feet up here and 8 feet up here, or 4 inches and 8 inches, whatever you want to think. But it would be a ratio of 1 to 2. That's the minimum ratio for no tip, assuming that this is your mu k. So not only does the friction force coefficient affect the angle necessary for a constant speed, but it also directly affects that ratio. So this is a neat little kind of like thought problem, thought experiment, whatever you want to call it. Okay, does anyone have any questions? Does that all make sense? Many of the problems you have on your homework, both in the lab manual and for mastering physics, you're going to want to use the lever arm method just like we did here, because it'll avoid needing to do all this kind of math. That being said, if you ever want to check your work, you've got this alternative method, and they should always give you the same result. So, okay, pretty tricky problem, pretty simple solution.
Quick question, Professor.
Mm-hmm.
For the second axis, can you explain one more time why we wouldn't want to choose that second axis on the bottom right?
Right, so the biggest thing is that when you choose this axis down here, what happens is that you eliminate the friction force and the normal force, right? Because they have no lever arm.
Mm-hmm.
And the only force you have left is the weight. So you'd have an equation that would look like, when you do your sum of torque equation, it'd be like mg times this distance r, okay, and then times the sine of some angle, and the angle in this case would be this really tiny angle right here, we'd call it alpha or something, equals 0. There's only one way to make this equal to 0, and that's to make alpha 0, and then you can't solve. There's just nothing to solve for, basically.
Gotcha.
Yeah. Be like if you had an equation that was like 2x equal to 0. Well, okay, x is 0. What's w over h now? So we kind of had to use these to get the w and the h in there, I guess is another way of putting it. But yeah. Okay, so all right. So this is weird because normally I want to just do 1 hour on Thursdays, but I really want to show you all this other problem because it's going to be one of the hardest problems on your homework. Maybe one of the hardest problems you do all year. I don't know. So I think what we'll do is we'll take a little 5-minute break, and then we'll do maybe 30 minutes on this other problem. It takes quite a while. Where is it? Oh, here it is. Oh, this problem is it's a beast of a problem. But what I'll do is I'll put it on the screen, and we'll take maybe we'll take a 10-minute break, I guess. I don't know. And then I'll do this one. And if any of you need to go, you can feel free to go, and I'll have this recording put up too. But I'll put it up on the screen. You can read this, maybe try to draw some free body diagrams. Just take 10 minutes. That'll give you plenty of time to read through it. If you want to just take a break and walk away, you can do that too. All right, so we'll take a break until 3:10.